Important that you have the microphone, so please just flag me if you'd like to ask something. Let's see. Yeah, Krissia, can you hear us? But we cannot hear you. Oh, this is a problem. And now we can't see either.
Hello.
Yes, now we hear you and see you.
Now you can hear me.
Yes, we hear you and see you now. Yes.
That's great. Thank you.
Great. Yes. So Krissia Zawadzki is our next speaker, and she will tell us about DFT-inspired approximations for quantum thermodynamics. Okay, please take it away.
Right. So good morning, everyone. I'm very grateful for being with you, not in person, but online today. I really appreciate the effort of the organizers and the support for enabling me to give this talk in this online format. I would love to be with you, but I couldn't make it this time. I'm looking forward for new opportunities to be with you in person and discuss some cool physics in this whole frontiers of quantum materials business. And talking about cool physics, the topic I selected to share with you today is a very special topic to me because it has a history which started back in 2017 at ICTP during a workshop titled Density Functional Theory Meets Quantum Information Theory. This event was organized by Vivian, who gave a brilliant talk yesterday about one-site entanglement in collaboration with Irene D'Amico and Klaus Capel. And this workshop was a milestone in my career because it stimulated me to start this, I would call it a research program dedicated to build approximations based on density functional theory to describe quantities which are extremely important within the context of quantum thermodynamics. And then it was nice for this workshop because then I started this fruitful collaboration with these folks, Irene and Vivian, and also Roberto Serra, who's one of the leaders in this field in Brazil, and also Marcela Herrera, who's now a professor in Colombia. But today, this is a really broad research topic, but a research program. But today I will be mainly sharing with you some results which have been published a couple of years ago in this paper, which was co-authored by Amy Skelt. At the time, she was a PhD student in New York, in which we first addressed a DFT-inspired approach to build specific approximations for what we call work and entropy in a thermodynamical setting. I will tell you a little bit more about what this business of quantum thermodynamics is, but I really encourage you all to take a look at this recently published roadmap in quantum thermodynamics on QTD and our perspective on what is the role of many body effects if you want to harness energy at the quantum scales. Okay, so this is the outline of my talk, of today's talk. I think for this audience it's really important to set a common ground and what are the goals and the foundations of quantum thermodynamics, why in the first place we need new thermodynamics to describe quantum systems, and how many body effects and strong correlations play a role, what we can say about the quantum thermodynamical limit. And then I will try to justify what are the complications that we find when we try to tackle many body out of equilibrium phenomena, and why would it be important to develop approximations to describe these quantities, mainly work entropy, and even I will tell you a little bit about the work distribution. I will show you finally our idea of a DFT-inspired framework to approximate these two quantities and try to convince you that this is a really promising framework by showing you a few results for driven ionic Hubbard chains. And then finally, to conclude, I will just share you some thoughts and perspectives and tell you what's the current state of the art in this research program. Okay, so starting with quantum thermodynamics. Thermodynamics, the classical theory we know very well. It was this well-established and robust framework to describe how energy converts and how we can harness energy for useful tasks. And then the question is, at which point in history people found out that we will need a new thermodynamic framework to describe quantum systems? And it's naturally to ask this question as we enter the first quantum revolution, which enabled, I think this community contributed very well to find new materials to build new technologies and devices, especially for computing power and communication, etc. But as we enter the second quantum revolution, we move to this new paradigm of, instead of just understanding how materials work, how we can manipulate quantum systems individually, how can we manipulate quantum properties to allow us to further push these new technologies to have some sort of advantage. I know that quantum computers are very popular nowadays, and there are a lot of discussions and debates about if they are really advantageous for many applications. But then I think this is a really nice overview and motivation to understand that as we try to now address the manipulation of quantum systems, we can also tackle the question of what are the thermodynamical consequences of manipulating quantum properties. Entanglement, superposition, coherence, these are all properties without a classical analog. And then many people ask me, okay, but quantum thermodynamics is solely a theory to say how energy works in quantum systems. We have thermodynamics is just a theory, a thermodynamical theory of few degrees of freedom. And then I will argue with you that no, and the main reason why is so is that now we want to use these properties, especially entanglement, as a resource to harness energy. And then we can think about optimizing the efficiency and energetically processes. For instance, we can manipulate a quantum phase of matter or activate a quantum phase of matter more efficient by using this toolkit of quantum thermodynamics. And then even if we are in the thermodynamical limit, we know very well quantum phase transitions are the most remarkable example that quantum fluctuations start to play a crucial role. And then all the properties that we want to understand, the consequences of quantum fluctuations to macroscopical properties and many body properties become very important. And quantum thermodynamics embraces this mission. So let's say that is now a fundamental field with, let's say, a practical appealing to build more efficient quantum technologies or carry out quantum processes more efficient than we do with the classical theory that we have for thermodynamics. But then to establish this field at the first place, it was necessary to establish the foundations and what are the definitions of work, what are the definitions of heat and entropy, the quantities, the laws, etc. And then on top of these foundations, we can start actually digging into this question of how we can build more efficient quantum processes and harness quantum energy or efficiency at the nanoscale. So then this is basically the idea of thermodynamics. And then to tell you why the many-body problem could be interesting and why phase transitions could be really nice to tackle within this framework, I will tell you a little bit about two quantities that will be mainly interested. One of them are the quantum work and the entropy and the definitions, how they are defined and why they are complicated in such a way that we can justify building approximations for these two quantities. Okay, starting with the quantum work. So work, we know very well in thermodynamics, classical thermodynamics, that is a controlled energy that we can extract or inject in a given system by means of an external control. And this is nothing in the quantum realm as a change, a time-dependent change that you can implement in your Hamiltonian. So imagine that you just change some order parameter in time, and then you assign this process a change in the internal energy of the system. This is as defined as in the classical setting as the quantum work. But one thing that happens that is a bit interesting and really important in quantum processes are, of course, quantum fluctuations, as I already told you. So you can imagine that if you start your system in a given state, can be an equilibrium phase, the equilibrium state of a given phase could be a ferromagnetic phase, for instance, and you want to drive your system across a different phase. You do this by a controller change in your Hamiltonian, and then during this process, the system experiences a lot of transitions between energy eigenstates, and this has a thermodynamic consequence. And the average energy that you have changed during this process is now is a 2-point difference, 2-point difference in the energy of the initial state and the final state. But all these transitions and their weight important very much, and that's why in quantum thermodynamics we say that work is not unobservable. But to characterize the work, the energy fluctuations that you have in this out of equilibrium process, you need a distribution in which work now has the role of an stochastic quantity assigned to the difference in energies between these possible transitions that your system may experience during this out of equilibrium protocol. And then this object is the main object to understand the energetical penalties of how fast you drive your system, how out of equilibrium you put your system. And to this aim, you basically address the work statistics. So the average of value of this distribution gives you how much work you can pump into the system, or your system can absorb. And the variance tells you how spread these fluctuations are, how probable are transitions between low line states and high energy states. And the skewness tells you how asymmetric those processes, those transitions, the energy of these transitions are. And there are already experiments addressing this distribution for a few spin systems, and nowadays people in cold atoms are trying to address this quantity, this object in a many-body system. But just there you can appreciate that just to characterize the energy, the energetic fluctuations in this out of equilibrium process, you need to account for a lot of many degrees of freedom, because these transitions grow exponentially with the size of your many-body system, right? Then I tell you already that the velocity, the speed that you decide to drive your system from initial state to a final state dictates how likely you are to have these transitions between different eigenstates. And this is quantified by the entropy. So how far from equilibrium you are depending on how fast you drive your system. And of course, if you do this protocol really slowly, you are close to equilibrium. This could be in a diabatic protocol, but as fast you go, you enter the situation of quantum friction. You're not guaranteed that your final state will be an equilibrium state. So this, in terms of, let's say, admixture of phase transitions, you'll be in a mixture of different phases. Suppose that you want to start from a not insulator and go to a metallic phase. You are not guaranteed to be in the metallic phase. In an informational framework, the entropy production, how is it quantified? It tells you how far from equilibrium, but how it's quantified? Well, in quantum info, It's just a relative entropy between the final state and what should be your equilibrium state. And then this already is a quantity that already tells you that it's hard to tackle these quantities experimentally and even numerically or analytically, because you need to fully tomograph a many-body quantum state, which is exponentially huge. But then there is an alternative way to estimate this quantity, which is by means of the quantum distribution itself. So you can estimate the average entropy production in this process by just having the average work, but of course you need the partition function, and this encompasses a lot of degrees of freedom. But an alternative way to address this quantity is by means of the fluctuation dissipation theorem and the relation, and then all the roles, your task will be estimating the work distribution, because the fluctuations, the variance of that distribution upper bound what should be the entropy production in this process. So these two quantities, which are standard in quantum thermodynamics, have been addressed in a variety of protocols with few qubit and small systems. But then people started to look into many-body phenomena, and it became very complicated because it's a lot of degrees of freedom to take into account when you want to understand, for instance, out of equilibrium phase transitions. So the struggle is real, because the many-body problem is complicated. More is different, but it's complicated. And then this is a good invitation for us to try to address many-body and out of equilibrium phenomena within the context of quantum thermodynamics, with the goal, the main goal is to recast these quantities in a simplified framework in terms of observables that we can actually assess experimentally. And this fundamental understanding will help us in the future, this is our dream, to understand more efficient pathways, let's say, to address phases of matter by means of quantum control. So this is the target, and this is the long-term goal. But at the first level, let's just try to simplify the description of these two quantities for many-body systems. And our idea, one nice idea, and I don't think I have to convince this audience that there are many theoretical approaches to tackle the many-body problem. And density functional theory is one of the most beautiful theories that we have available to do so. I know some people will say, okay, but if you are in the local density approximation, you are close to Hartree hell, and as you move to more strongly correlated phenomena, you are far away from the heaven of chemical accuracy. But regardless of that, should appreciate that DFT is a really successful theory, and most of our knowledge of the electronic structure of materials came from this beautiful theory. But this is at a practical level. But I would just like to call your attention to appreciate the beauty of the foundations of density functional theory and its potential to help us to address the many-body problem. So I'd like to recall you the whole Hohenberg-Kohn theorem, which is amazing because it basically gives us this nice framework to move from the wave function, a many-body object, exponentially large, to simply the density, and this can be the local density, this very simple observable, extremely available, widely available in many platforms for many-body physics. And then just by having the local densities, as long as you can express observables as functionals of the density, and we have the density, we have everything that you need. So this is really powerful, and this is something we are going to pursue in this toolkit of building DFT approximations for quantum thermodynamics work and entropy. And on top of that, another amazing idea of within the framework of DFT is the conscience mapping, which tells us that we can, in principle, represent any many-body interacting system in terms of an effective non-interacting Hamiltonian, as long as we have the so-called exchange correlation functional. But this is exact, but let's say that we don't have all the functionals. But if you have a good approximation for the exchange correlation functional, we can just rely on a non-interacting framework, almost as powerful as mean field, and we have all the physics there. So this is really powerful, and this invited us then to start those approximations for work and entropy. So I defined work and entropy. So as I said, the work is just the difference between the initial and the final energy states, the average work that I can extract. Of course, this object is extremely complicated. These two are many body, both the Hamiltonian and the density matrix are both many body objects. The entropy contains two many body quantities, the partition function and the average work itself. But building on these two quantities, we can ask how we can use DFT to approximate, to build some approximations for these two quantities. And our idea was basically to identify three crucial ingredients to build approximations within this framework of conscience DFT. And we found, okay, so here, basically, I need a good approximation for the initial states that I want to time evolve. Then I have let's say the first term, the energy at the very beginning of the dynamics. I can also have an approximation for the many-body Hamiltonian, and for that I will use the conscience Hamiltonian to kind of replace the complicated many-body Hamiltonian, the many-body model. And then as a consequence, the final state and the final energy that I would, in principle, extract or inject in the system is a consequence of the two choices that I made for approximating the initial state and the dynamics. So then, based on these two ingredients, the initial state and the dynamics, we proposed the two levels of approximations, which we will call simple and hybrid. And what they are, so the simple approximation basically uses the same approximation, the conscience approximation, to build the initial state. So here I'm using the conscience Hamiltonian to build an approximation for the initial state, and the conscience Hamiltonian to time evolve this initial state, and then use these two objects to obtain an approximation for the average energy that changed during this process. In the hybrid approximation, I will assume that I have a good approximation for the initial state, for the many-body state, which is correlated, entangled, and so on. And then I will use the conscience Hamiltonian, the time-dependent conscience Hamiltonian, to time evolve the system. And then I can compare what's the penalty of not having a good approximation for the initial state if I solely work with no interacting framework for the dynamics. So these are the two levels, and we are going to compare them. And then I can think, okay, so my no-interacting Hamiltonian doesn't contain any Coulomb repulsion or interaction at all. Then I have an external time-dependent potential that will drive my system across some different phases, doesn't contain interactions. And in this, at least for dynamics which are described by this, I will approximate these first two terms by the conscience Hamiltonian, let the external control evolve as it wishes, and then I will compare what happens if I decide to not approximate the initial state, or even have a good approximation for the initial state. So these are the two, let's say, the levels of approximations that we can build within this DFT framework for thermodynamics. And okay, then you ask, okay, but then you need to build the constant Hamiltonian, you need an approximation for the exchange correlation potential. And then I will tell you that I will be working with the Hubbard Hamiltonian. I imagine that Vivian already told you that there is a nice DFT approximation for the exchange correlation potential of the Hubbard Hamiltonian, which was built from the exact Bethe-Ansatz solution for the homogeneous system. And then you'll be mainly using this approximation to test how good we can describe work and entropy in an out of equilibrium process. Okay, and another alternative that we have that is useful for one-dimensional systems is not all is a DFT VXC, but there is a theorem for one-dimensional systems which allows you to obtain the exact constant potential as long as you have the exact densities. You have a reverse engineering scheme that allows you to obtain the exact VXC by just having the exact results. Of course, you need the exact results to have the exact exchange correlation potential, but we need to just test if the idea that if you have a good functional in principle, we will have a good approximation for these two thermodynamical quantities. And the model we are addressing these two questions, in which we'll be addressing these two questions, is the driven ionic Hubbard Hamiltonian. So basically just have hopping and Coulomb repulsion in this case. So, and then you have this staggered local potential plus minus on each side in such a way that you move from a Mott insulating phase or metallic phase deep into a band insulator. And one of the consequences of this change is that you change the level of statistics from GOE to Poissonic. We will be mainly discussing this protocol and this model starting from either the metallic or the Mott insulating phase deep into the band insulating phase. Let's take a look at the results. So the results we will be comparing are two levels of approximations using a fully non-interacting description, the Bethe-Ansatz local density approximation functional, and this reverse engineered exact potential that we can obtain as long as we have the exact solution of the system itself. Okay, then it's important to say that our approximation are statics in the sense that if I build the constant Hamiltonian just at t equals 0, and then all the time dependencies are carried out through this external control field that I turn on in time. Okay, but I will discuss how we can improve this approximation by incorporating time dependency explicitly in the constant potential. Let's take a look at the results. So this is first the results for a fully non-interacting approximation. And on the top line, I show you the simple approximation. So I'm using a non-interacting initial state and a fully non-interacting Hamiltonian to move my system from a phase to the other. Here I show you initial state prepared at very high temperatures and very low temperatures. And as expected, nothing is new. So the more blue, the better is the approximation is the following. So here I see that, okay, I use the same fully non-interacting approximation at low temperatures. Quantum effects quantum correlations are extremely important, especially as I increase the value of the Coulomb repulsion, because then I enter the Mott insulating phase. And I also have this phase competing with the ionic potential. And then I'm not able to obtain a good result for just the average work, just the energy. But if I have a good approximation for the initial many-body state, which is the bottom line here, even if I'm at a very low energies, very low temperatures, I'm able to recover the average work with less than 20% of error with respect to what will be the exact result, the exact average work. Then we can compare with Bauda. And then this is the Balda and the GKS and just the simple approximations. So I can show you here. So here, high temperatures, I see that Balda kind of spoils the initial state, and the reverse engineering potential also spoil at higher temperatures. But then at least there are some regions, some correlation regimes which are reasonably well recovered by just considering the Conshan approximation for the time-dependent Hamiltonian. Now, if you compare with the hybrid approximation, so now I show you that Balda is kind of good in the weakly coupling regime, but as you move to the from the multi-insulator to the ionic phase, you kind of struggle regardless of the temperature. But with reverse engineered scheme is really nice because as long as you have a good approximation for your initial state, you are able to recover the average value of work with the Conshan Hamiltonian to describe your time-dependent dynamics. So this is really powerful and this is really promising, at least for the work. And what is happening there? Okay, so then you can ask, what's happening there? And then, at least for the time dependency, so forget about the initial state, just consider what happens with the object, the time-dependent Hamiltonian that you use to time evolve your system and describe the dynamics. And you just have to take a look at this spectrum. And we see for this the weakly coupling regime, the spectrum of the exact Conshan Hamiltonian and the Balda kind of reproduces really well the spectrum of the many-body exact Hamiltonian. As we go more and more into the correlated regime, our spectrum started to get spoiled. Balda completely overestimates the energies, at least in the beginning of the dynamics, and the Conshan inverted Hamiltonian starts a little bit well if you are at low temperatures, because these are the states that will contribute to your dynamics. But the high energy states and high energy fluctuations wouldn't be really approximated. But as long as you are close to this, let's say that your dynamics is dictated by these low-lying energy states, somehow you have a reasonable description for that. That's why this approximation goes really well compared to Balda. If you increase correlations, both spectrums are terrible. Okay.
Sorry
so
to interrupt.
This is
Can you hear us?
The main message.
I just wanted to give you a warning that you have a little bit less than 10 minutes left, which includes the time for questions.
Okay, sorry about that. Yeah. Okay. Oh, okay. So this is okay. I will finish in 2 minutes. Sorry about that. So these are we can compare these approximations. So and say, okay, I want to select from all these approximations that you consider, and here is a comparison between that for the entropy. And so, but I think I gave you the main idea, right? So basically the story I wanted to tell you today was that if you want to address many body systems out of equilibrium, it will be amazingly nice, and it will be really promising to try to build some approximation, and DFT is a nice way to do so. I discussed these two potential approximations, the hybrid and the simple. And I show you that at least as long as you have a good initial approximation for the initial state, and if your external potential or external control field is not accounting for correlations, say Coulomb repulsions, these approximations will be really good to approximate the work distribution and the work statistics. And then you can ask, can you further improve that? And then I think I will invite you to go to see one of my students' poster, which is Orion Villanova. He's presenting a poster on how you can further improve these approximations by incorporating time-dependent exchange functionals within the Conshan time-dependent Hamiltonian, and also time, the thermal dependence on the initial state. And thank you, sorry for the time, but thank you so much for your attention. And I'm looking forward to take any questions.
I hope you could hear the clapping. So yeah, we have time for a few questions, so please. Okay. Maybe then I can start. So just a totally basic question, and maybe I just missed it in the beginning. So, you know, in ordinary thermodynamics, we have laws that are very, you know, general and universal, and that's kind of where the theory derives its power. I mean, in this framework that you're trying to develop, is there some similar set of universal principles? Like what happens to the second law of thermodynamics, for example? Is there any version of this that still survives?
Yeah, there are many flavors of the second law of thermodynamics at the quantum scale. And there are some debates on how you actually define entropy and what will be the role of entanglement in defining what is the thermodynamical entropy. But for instance, one of the latest works we're dealing with, this is the same framework that we have here. So you have an isolated system. It's not interacting with any thermal environment. You drive the system out of equilibrium. Would you expect to produce some entropy? So this is how you recover it. So this is one way you can say, okay, I just see how far from equilibrium I will be, thermal equilibrium, or it can be a steady state, and that will tell me that I produce entropy. But yeah, there are many flavors of the first and the second law and different definitions of these quantities, depending on the protocol that you are using in the system.
I see. Okay, thank you. Anybody else?
Yeah. Hi, Krissia. I'm not sure this could be a super silly question because I don't know much about DFT, but if I understood correctly, you do an approximation and you do the comparison with the exact result. Now, is there an a priori way to guess if the approximation is going to be good or bad on general ground or what? I mean.
Yes. Well, if you are in a regime in which you are, let's say, if you measure correlations between neighboring sites in a spin chain, for instance, in principle, LDA and GGA-like approximations for your exchange correlation potentials will make the deal. So they will be well. But if you have long-range correlations, then you will need something else. So let's say then at least measuring entanglement, local entanglement, and long-range entanglement will be a nice way to just say how good the choice of your VXC will be.
More questions? One more question.
Hi, Krissia. Thank you for the very nice talk. So, very basic question. You told us that your constant approximations get worse as temperature increases because of time-dependent correlations. So, I was just curious. Could you tell us a bit more about that? Because, in principle, if you don't have temperature or time, constant scheme captures all the correlations of the system, right? So how does it interplay with these time-dependent correlations, and how does I think it's related to what your alumno, I don't know how to call it, what your student is trying to implement to get the time-dependent correlations in the constant functional. So.
So your constant doesn't have the Coulomb repulsion, right? So you just mimic it through the exchange correlation potential. But then when you change your Hamiltonian in time, regardless of this being the Coulomb repulsion, the value of U in time, or an external potential that in our case is just that ionic staggered potential, you change the whole set of eigenstates and energy states. So here I show you, this is let's say this is the ground state evolving in time, because I'm changing my Hamiltonian. This is the first excitant. So all those states, their energies are changing in time, and their internal structure are changing in time. But to read, and in this first approximation that we build, we basically just consider the VXC as that one for the Hamiltonian at t equals 0, and we just evolve those staggered potentials. So to really increase the accuracy in reproducing this spectrum, the energies itself, you need to incorporate explicitly the time dependency on the exchange correlation potential. So let's say that the first level approximations, the Constant Hamiltonian was just constant at time equals 0 plus V of t. And now we want to do just the hoppings plus the constant potentials depending on the time, because the densities are changing in time as well. So that's why we need to add this external dependency explicitly on the time-dependent densities to improve the description of the energy levels evolving in time.
Great. So let's thank Krissia again for a very nice talk.
Thank you.
Okay.